before I begin to tell you the essence of what is a derivative of a function, or I tell you how practically the derivative of a function is practiced and you will be able to see it and observe it and feel it as well. Let's begin with the dry definition of what a derivative is, and then we are going to learn about its physical interpretation and geometrical interpretation as well, which is going to make us realize the real form, the real meaning of what is the derivative of a function. So primarily this particular article deals with functions, and secondly, now that you have done limits, this particular portion will be using your entire theory, your entire knowledge on limits. So you should be very aware about how does a function behave, and you should be very aware about how does a limit of a function at a point behaves, what are its characteristics, what are its properties, what are its different forms, everything you should be aware about before studying derivatives. So let's begin this, and then we'll proceed to actually learn how to visualize a derivative. So let's start. Firstly, it demands that let f, the function which is coming into picture, it is saying that let f be a real valued function. Let f be a real valued function. So what is it saying? Let f be a real valued function defined on an open interval a comma b. So when it is saying that let f be a real valued function defined on an open interval a comma b, that means what is this trying to say? It is saying that this interval a comma b is acting as the domain of f, and because it is real valued means what? Because it is real valued, this means range of f is a subset of collection of all reals. Yes, that is what is the meaning. If f is a function which is real valued defined on this set, that means for all members sitting inside this open interval, for every small x sitting inside this open interval, f of x exists. Understood? For every x belonging in this open interval a comma b, f of x exists, right? That means this is the set of valid inputs for the machine f. Fine? Now, when I am saying f of x exists for every x in this open interval ab, that f of x is actually existing to be a real number. That means, and why am I able to say that? Because f is real valued. So for every x in the interval a comma b, f of x exists to be a real number, and the collection of all the f of x's for every x in the domain is nothing but the range. And I have written, because it's given to me that f is real valued, that range is a subset of real numbers. That means every element sitting in the range is actually a real number, and every element sitting in the range is nothing but the output produced by the machine f corresponding to the inputs coming from this open interval. That means for every x in this open interval a comma b, f of x is a real number. Understood? So a comma b is the domain, all the points for which f is defined, and f of x, the set of all the f of x's, is nothing but the range, which are real numbers. Understood? So f is a real valued function defined on the open interval a comma b, and let c be some point in this open interval. Fine? So for all x belonging to a comma b, f of x is defined to be a real number, right? So for a specific point in a comma b, which I have denoted by c also, f of c is a real number, it is defined. Fine? So, and let this be some specific point of the domain of f. C is one specific point among all the points for which f is defined. I have chosen one specific point c in the domain of f, a comma b open interval. So, and let c belongs to a comma b, then f is said to be differentiable at point x equals c, or f is said to be possessing a derivative at the point x equals c if and only if. What happens? Well, I have written, if f is defined for an open interval a comma b such that f is real valued, then if you pick up any point on this open interval, for every point of the domain of f, you can check whether the function is differentiable at that point of the domain or not. Corresponding to every point in the domain of f, you can check one question being answered yes or being answered as no. That f is differentiable at a point of the domain or not, or I can say f is having or possessing a derivative at that point or not. When can you say that if c is some specific point of the domain of f, then f is differentiable at that point or f is having a derivative at that point? We can say that if and only if limit x approaches to c, fx minus fc upon x minus c exists finitely. That's the meaning. So for every point c in the domain of f, you can check whether the limit of this function exists finitely or not. When I am saying exists finitely or not means what? See, f is a real valued function. So for every x in the neighborhood of c, f of x is a real number. c is already coming from the interval a comma b, so c is a real number. That means f of c, because f is real valued function, f of c is already a real number. So fx for every x in the neighborhood of c is a real number, f of c is a real number, x, c both are real numbers. So here this is a real valued function. So when I am saying the limit as x approaches to c, this function approaches to what point? Right? So if this limit is existing finitely means that the limit, that means the limiting value of this function as x approaches to c, the limiting value, that value if comes out to be a finite real number, only then can I say that this limit is existing finitely. That means it should come out to be a finite real number. It should not come out to be infinity, it should not come out to be minus infinity, or I can say it should not come out to be a case in which I have to say that the limit does not exist. No. Leaving these three cases, all other cases give me the limit as a finite distinct real number. In those cases in which as x approaches to c, this function approaches to a finite real number, I say that my function f, real valued function, is differentiable at this specific point of the domain which is c. Understood? This is the definition of f being derivable or f being differentiable or f possessing a derivative at the point c. Fine? This is what is the definition. So I'll say let f be a real valued function, that means corresponding to every point in the domain, f is giving real values as the images. So for every x in the open interval ab, f of x is a real number. Fine? So let f be a real valued function defined on this particular open interval a comma b standing to be the domain of f, and let c belonging to a comma b be a specific fixed point in the domain of f for which f of c is defined to be a finite real number. Fine? So c belongs to a comma b be fixed, then f is said to be differentiable at point c, or f is said to be possessing a derivative or having a derivative at c if and only if this holds, if and only if this limit exists as x approaches to c. Fine? If this limit The first question is talking about limit. It says limit x tends to pi by 6. What is the value of this particular function? Now see, over here it's pretty simple to understand. The numerator will be broken as 2 sine square x plus 2 sine x minus sine x minus 1, right? And the denominator will be broken up as what? 2 sine square x minus 2 sine x minus sine x plus 1, and you need to evaluate the limit as x approaches to pi by 6, right? So what happens in the numerator? Your 2 sine x comes out common. You are left with sine x plus 1 minus 1 sine x plus 1. In the denominator you have again 2 sine x common, sine x minus 1 minus 1 sine x minus 1, and again limit as x approaches pi by 6. So clearly you can see you have sine x plus 1 into 2 sine x minus 1, sine x minus 1 into 2 sine x minus 1. 2 sine x minus 1 gets cancelled from the numerator and the denominator. You are left with sine x plus 1 upon sine x minus 1. You know that this is continuous, denominator is not vanishing at pi by 6, so I am just going to incorporate the very value of x equal to pi by 6 to get the limit. Now what I get is 1 by 2 plus 1 upon 1 by 2 minus 1. So you get what? 3 by 2 whole upon minus 1 by 2, which brings the answer as minus 3. So the limit of this expression very easily can be calculated by just breaking the middle term and then solving the expression to get the value of the limit as minus 3. Next question says what? It says if the value of this particular expression is 100, then what is the very value of n for which this is 100? So over here, very nicely I can talk about the application of this result, that limit x tends to a, x to the power n minus a to the power n whole upon x minus a is n a to the power n minus 1, right? How can I apply this result over here? See, look at the expression, limit x tends to 0, 1 minus x to the power n minus 1. Now this 1 can be written as 1 to the power n, not a problem, right? Then you have in the denominator you have x. So basically to create 1 minus x, you write it as 1 minus x minus 1. But when you resolve this, you actually get minus x in the denominator, right? You get minus x in the denominator, not x in the denominator. This value is given to you as 100. So minus of this value is going to be equal to minus 100 because there is a minus sign extra. And now things are completely replicated as per this. Why? Y to the power n minus a to the power n whole upon y minus a, I only need that y should tend to a. So if I take 1 minus x equals y, I have y to the power n minus a to the power n whole upon y minus a. What I just need is limit y approaches to 1, and that is very simple. If x is approaching to 0, if x approaches to 0, minus x also approaches to 0. So 1 minus x approaches to 1, that means y approaches to 1. And this is exact copy of this. This is n into a to the power n minus 1. This thing is given to you as minus 100. So this expression is n into a to the power n minus 1 is minus 100. That means n is minus 100, and therefore your answer is option number B, that is minus 100. The next question says that the value of this particular limit is what? Okay, so let's try to evaluate. So all types of questions we would be watching in limits. Over here, if you see, Now this is pretty nice. This is x tends to infinity. Whenever x is tending to infinity, we try to bring all x and powers of x in the denominator, so that as x tends to infinity, 1 upon x tends to 0 and the world is simplified. So what we do in here is, we basically try to take out x square common, and from the square root, when x square comes out common, it becomes obviously x. So I basically write it as x square. Inside I have 3 minus 1 by x square plus under root x square 2 minus 1 by x square. In the denominator also, I don't want x over here, I am going to take it in the denominator then. So I have x common, 4 plus 3 by x. Very clearly, square root of x square is going to be x, square root of x square is going to be x, so x is going to come out common from the entire numerator and get cancelled. I have limit x approaching to infinity. So now what you are left with is under root. Now if you put x equals infinity, as x approaches infinity, 1 upon x approaches to 0, 1 upon x square approaches to 0. So this expression is just root 3. Similarly, this is root 2, and in the denominator it is a 4. Because as x approaches infinity, 3 upon x approaches 0, minus 1 upon x square approaches 0. So this is what you are left with, and therefore when you rationalize it, what you get is root 3 plus root 2 into root 3 minus root 2 by 4, which becomes what? 1 upon, here also you will be multiplying this expression. This will be 1 upon 4 into root 3 minus root 2, and that is your answer. Clear? Pretty easy stuff. Then we have the value of limit of this expression is what? Okay, so let's evaluate. Limit n tends to infinity of this expression. Now see, you can see this is 1, 2, 3 and so on up till n. And then there is 2, 3, 4 and so on up till n plus 1. Whatever is n, one more is the adjacent term, right? And that is happening in every term of this expression. So I can write this as what? Limit n tends to infinity r, or let me write summation r into r plus 1, r going from 1 to n. For r equals 1, this is 1 into 2, plus for r equals 2, it is 2 into 3 and so on. For r equals n, it is n into n plus 1. So what you get in here is, this is limit n tends to infinity summation r square plus summation r. You know the value of these summations? This is limit n tends to infinity, this is n into n plus 1 to n plus 1 by 6, right, plus n into n plus 1 by 2. Fine. So over here, very simply what we can do is, I can take out the LCM. What I will be left with is n into n plus 1 to n plus 1 plus 3n times n plus 1 whole upon 6. Fine. So this becomes limit n tends to infinity, limit n tends to infinity, n into n plus 1 is going to come out common. You will be left with 2n plus 1 plus 3. 2n plus 1 plus 3 means 2n plus 4 whole upon, this is what? N into n plus 1, 2n plus 1 by 6, and this is what it is, and over here you have n cube also in the denominator. So this becomes whole upon n cube, this is whole upon n cube, here also you have n cube. So numerator becomes this, denominator you have 6n cube. So n gets cancelled out, you have limit n tends to infinity, n plus 1, 2 comes out common, you have n plus 2, 6n square. This is 2 gets cancelled out, this is 3. From here again, because n is tending to infinity, I would want it to come in the denominator. N comes out common, I get 1 plus 1 by n. Another n comes out common, I get 1 plus 2 by n whole upon n square. 3n square. Right? This gets cancelled out as n tends to infinity, this tends to 0, this tends to 0. So, you get 1 by 3 as your final answer, and that is what is your very correct option. That is how you compute this limit. The first question says limit x tends to 0 of this expression is what? Now see, the moment you see 1 minus cos 5x and in the denominator you have 1 minus cos square x, right? So, in the numerator you can very easily dissolve this into, this is 1 minus cos x, you know this, how do we expand this? This is 1 plus cos x plus cos square x plus cos cube x plus cos to the power 4x whole upon 1 minus cos square x is what? 1 minus cos x into 1 plus cos x. Very clearly this gets cancelled out. As x approaches 0, we have cos x approaches 1. So, limit x tends to 0 of 1 is 1. Limit x tends to 0 of cos x is 1. Limit x tends to 0 of cos x whole square is limit x tends to 0 of cos x then whole square, which is 1 square, which is 1. This is 1 cube, which is 1. This is 1 to the power 4, which is 1 whole upon 1 plus 1, that is 2. So, you basically get 5 by 2 as your very limit. Clear? Moving on to the next question, we have limit x tends to 0 of tan x minus sin x whole upon x cube. Let's try to see what this limit turns out to be. Tan x minus sin x. Okay, so tan x minus sin x whole upon x cube. Okay, so this becomes sin x upon cos x minus sin x whole upon x cube. Limit x tends to 0. I am just dissolving everything in terms of sin and cos. So, this lands you to the step sin x minus sin x cos x whole upon cos x into x cube. Fine. Next step, you can see from the numerator I can extract out sin common. So, I get sin x common and inside I have 1 minus cos x and in the denominator I have cos x into x cube. And clearly this is limit x tends to 0. Now what I do is I basically distribute this limit to simplify my expression. I get sin x upon cos x and I basically put x cos x here. 2 x's are remaining, I just keep it as another expression which is 1 minus cos x upon x square, which is 2 sin square x by 2 upon x square. Now you know that limit x tends to 0, sin x by 2 upon x by 2 is 1. I want x by 2, so I basically divide by 4 and multiply by 4. So that I get x by 2 whole square and here I have sin x by 2 whole square. So here basically this turns out to be limit x tends to 0, sin x upon cos x is tan x by x into 2 by 4 comes out, that is 1 by 2 comes out. It's a constant independent of x. Then you have sin x by 2 upon x by 2 whole square. You know square is a continuous function. So limit of this square is square of limit of sin x by 2 upon x by 2, which is square of 1, which is 1. So this you know is 1 into 1 by 2 into this is 1 square, which is 1. So your answer is nothing but 1 by 2. Clear? Moving on to the next question, we have what is the value of this particular limit? Now here if you carefully observe, the main expression which is playing the role is 1 plus x whole to the power 1 by x. So let's catch hold of that term and then try to resolve the entire expression on the basis of 1 plus x whole to the power 1 by x. Now here if I catch hold of this complete term, I am saying let y be equal to 1 plus x whole to the power 1 by x. You know, in order to bring this 1 by x ahead, I need to bring log into picture. So I bring log into picture, I say that log y is 1 by x log of 1 plus x. This is actually log of 1 plus x whole to the power 1 by x, which becomes 1 by x log 1 plus x. Very well versed with the expansion of log of 1 plus x. What is it? It is x minus x squared by 2 plus x cubed by 3 minus x to the power 4 by 4 and so on. Just multiply this inside, you get x upon x, which is 1, minus x upon 2 plus x square upon 3 minus x cube upon 4 plus and so on. This is nothing but log y. So y will be equal to what? Y will be equal to e to the power 1 minus x by 2 plus x square by 3 minus x cube by 4 and so on. Now e to the power 1 plus minus x by 2 and so on can be basically resolved into e to the power 1 into e to the power minus x by 2 plus x square by 3 minus x cube by 4 and so on. Here now I am going to use the expansion of e to the power something which is 1 plus that something plus that something whole square by 2 factorial and so on. Don't forget, I am interested in limit x tends to 0 of this expression, okay? Don't forget that. Okay, coming back, how can I resolve this? This becomes e minus ex by 2 plus ex square by 3 minus ex cube by 4 plus and so on, and then you have e again. So e by 2 factorial. So this is the next term, another term. This is e by 2 factorial. Inside you have minus x by 2 plus x square by 2 minus x cube by 3 and so on whole square. So from here you can take out x common. When you take out x common throughout, actually x square comes out. And inside you are left with minus 1 by 2 plus x by, this is minus x by 2, this is 3 and this is 4. So you are left with minus 1 by 2 plus x square by x by 3 minus x square by 4 and so on. Now you can see I can write this as y minus e plus ex by 2 equals, from here you are left ex square by 3 and so on, then again ex square by 2 factorial into all of this. So I can see that ex square is coming out common. I am left with 1 by 3 minus x by 4 and so on, plus also I am left with ex square common, so I am left with 1 by 2 factorial. So this is one thing, complete ex square is coming out common. I am left with 1 by 2 factorial times, this is common, okay, so minus 1 by 2 plus x by 3 minus x square by 4 and so on, okay. So from here you can see I can just bring x square over here. This becomes y minus e plus ex by 2 whole upon x square, okay, and here you are left with e into all of this. Right, x square only I have extracted to bring it down. Now that I have extracted x square to bring it down, I want, this is y minus e plus ex by 2 whole upon x square. So that I have got on the left hand side. See, y minus c plus ex by 2 whole upon x square. I am just interested in the limit. Limit x tends to 0. Y is nothing but 1 plus x whole to the power 1 by x. Let me replace that by the expression y minus c plus 1 by 2 ex whole upon x square. When you apply limit x tends to 0 on the right hand side, it is e into all of this. Limit x tends to 0 makes all of this 0. You are just left with 1 by 3. Here it is square of this, all this is square, right? So square gets carried forward. Here when you apply, all these terms become 0. You are just left with minus 1 by 2 whole square, which is 1 by 4 into 1 by 2 factorial, which is 1 by 8. So you're just left with e multiplied by 1 by 3 plus 1 by 8. Yes, just left with e multiplied by 1 by 3 plus 1 by 8, because rest all the terms contain x. So when x approaches 0, all those terms become 0. And 0 plus anything is that thing itself. So this gives you 11 by 24e. So your answer is option number A. Clear?